Let's take some time and talk about how to solve equations, and then eventually we're going to look at inequalities as well that involve absolute value. Now, first as a reminder for the definition, the absolute value of a number n equals the distance from the origin to the point whose coordinate is n. So we are going to be working on like just a real number line. So when we're talking about the absolute value of a number n, mathematically we notate that by putting the number between two vertical bars. All right, and I always like to try to make sure my vertical bars are noticeably longer than the number inside so they don't look like the number 1. So that's how we notate that I want you to find the absolute value of a number. So when we're working on the real number line, when we talk about the origin, this is the same thing as 0. Okay, so it's the distance a number is from 0 on the number line. And when we're looking at this idea about distance, the distance is always going to be non-negative, which means it could be 0 or some positive number. Now, in physics, in some sort of science application, sometimes they will do a signed distance depending on what the point of origin is, but for our purposes, we're going to say distance is going to be non-negative. Okay, so as an example, what if I asked you to find the absolute value of -4? So that is asking you on a number line, where is -4 and how many units is that number away from 0? So here is -4. So if I look at from -4 to 0, it is 4 units away. So we would then respond that the absolute value of -4 equals 4. I don't care that it was 4 units away to the left, I just care that it's 4 units away. Right? So we're always going to be thinking about this idea about distance. So let's talk about solving absolute value equations first. So what we're going to be seeing in the problems is that our variable is going to be inside the absolute value bars. And then we're going to be finding the value for the variable that makes that equation true. For our first example, I have the absolute value of x is equal to 5. So this problem is just kind of asking us, this is saying what value or values, if there's more than one, have a distance of 5 units from 0. Okay, so we're always going to think about that absolute value as being distance away from 0. So this is going to be what numbers can I put in right here for x as being a placeholder that have a distance of 5 units away from 0. So, on my number line, you can say, okay, well, if I want to go 5 units away from 0 to the right, that number would be 5. And if I wanted to go 5 units away from 0 to the left, it would be -5. Okay, so we get two possible values that I can put inside the absolute value bars that would satisfy this equation, 5 and -5. So for this second example right here, the absolute value of k is equal to -4. This is asking me what values have a distance of -4 units from 0. Okay, and here is where we encounter the problem, right here. Distance is going to be non-negative. So it can be positive or it could be 0, but distance cannot be negative. So the nature of what's being asked here, this question, doesn't make any sense. So what values will satisfy this distance requirement? Nobody will. So we would respond to no solution. Right? So the issue right here is the sign. Right? It's the fact that I have this negative over here. This doesn't make any sense. All right, last example. The absolute value of w is equal to 0. So this is asking me what values will have a distance of 0 units away from 0. Kind of a silly question. Who is no units away from 0? It's going to be 0 itself. So the values I can put in for W are 0. So we're seeing for these absolute value equations, we could either have 2 solutions, 1 solution, or no solutions, depending on what's going on inside the problem. Okay, so in general then, to solve absolute value equations, the absolute value of u is equal to a. This is how the equation will be presented to us. This is going to be equivalent to u is equal to a or u is equal to negative a. So we're seeing then we have these 2 cases that we'll be able to solve. Now just as a side note, this absolute value equation, this only makes sense if a is greater than or equal to 0. If a is less than 0, the absolute value of u is equal to a, will have no solution. So you could then report that the solution is the empty set. One of the things to notice that when we have this equivalent idea is over here, I want you to note that there are no absolute value bars. And that's important. What we're trying to do is we're trying to take this expression that's inside the absolute value bars, and we're trying to write it as something equivalent where we no longer have those bars. Those bars are kind of acting like as like a trapping mechanism, preventing me from getting to my variable. So we're going to break it into these 2 cases and then solve these 2 cases where I have no bars. So just generally the steps to solve these. The first step is to isolate the absolute value. That means get it by itself on one side of the equation if it's not already by itself. We're going to write 2 equations, one using the positive value of the constant a, and then the other using the negative of a, and then we're going to solve each of the resulting equations. All right, so that was a lot, so let's work through a couple of examples so we can look at what that means. So for our first example down here, I have the absolute value of 4x plus 2 is equal to 6. Now the first thing is to notice that my absolute value is already isolated. Okay, so my step 1 is done. It's all by itself on one side of the equation. On the other side of the equation, I want you to notice that this is a positive number. Okay, so it's not negative. So it does make sense to solve this question. You want to kind of ask that at the beginning because you want to know before you get too far into the problem, does it even make sense? Is this a logical question for them to ask me to solve? And in this case it is, because that's positive. Right? So because that's positive, what we're going to do is we're going to break this into our 2 cases. Now because there's 2 cases, I like to actually draw 2 sets of arrows to indicate that this is now going to be 2 cases and I'm going to have to solve each case independently. Now the first case is usually the one that most students tend to remember because it's the one where you're going to rewrite the problem and you're just going to drop the absolute value bars. Okay, so that case is equivalent to this. Okay, so it's just going to be, I'm going to take this expression that's outside of the bars, I'm going to drop the bars, and then whatever number here I set on the other side, I'm just going to repeat it. Right, so that's case 1. That's easy case. The other case that you cannot forget is going to be 4x plus 2 is equal to negative 6. So for my second case, what we're going to be doing is we will leave the expression inside of the absolute values bars alone. Right, so we don't touch that expression. What we do is we change the sign of the number on the other side. That gives me my second case. Don't forget that case. Now we solve each one of these cases independently. So for this first case, the 4x plus 2 is equal to 6. We'll subtract 2 from both sides. We get 4x is equal to 4. Divide both sides by 4. X is equal to 1. For my second case, subtract 2 from both sides. We get 4x is equal to negative 8. Divide both by 4. X is equal to negative 2. So in this case, I have 2 solutions that if I wanted to, we could write it into a solution set. Right, so my set notation is going to use the braces, and then I'm just going to list what the values are that would make this equation true inside my set with commas in between them, and then just close my set. Alright, so that's what it looks like to solve these absolute value equations. So let's try that again. On our second example, it's going to be the absolute value of x divided by 3 plus 4, close the absolute value, plus 2 is equal to 3. So on this one, our first step, isolate the absolute value, is not already done, so we're going to have to do that. So the first thing we're going to do is we're going to subtract 2 from both sides, and I get the absolute value of x over 3 plus 4, close my absolute value, is equal to 1. Now a couple things to note here. Do not drop the absolute value bars just yet. You're not dealing with them at this point. All you're trying to do is isolate that absolute value expression on the one side by getting this number to the other side. All right, so that's the first thing. Don't drop those bars just yet. We'll drop them on our next step. The next thing is now we can assess what number is on this side. So we can't look at the number right here because the absolute value wasn't by itself. So now that it's isolated, I can look at this number over here. I can see that it's positive. So because that number is not going to be negative, it makes sense to actually go ahead and solve this. So we're going to break this into our two cases. The first case is the easy one. It's the x over 3 plus 4 is equal to 1. So it's the original problem, just drop the bars. Don't forget the second case, x over 3 plus 4 is equal to, and then you're going to take the negative of the number that's on that side, so negative 1. There's my second case. Alright, so let's just go ahead and solve those. For the first case, subtract 4 from both sides. We'll have x over 3 is equal to negative 3. Multiply both sides by 3. We get x is equal to negative 9. In the second case, we'll subtract 4 from both sides, so x over 3 is equal to negative 5. We multiply both sides by 3, we'll get x is equal to negative 15. All right, so my solution set is negative 9, negative 15. All right, for the next example, 3 absolute value of y, and then close the absolute value, plus 26 is equal to 17. All right, so you have to isolate that absolute value first before I can really do much to deal with the absolute value part of this. So the first thing we're going to do is we'll get this number to the other side by subtracting it. So we'll subtract 26. We get 3 absolute value of y is equal to negative 9. Now because this 3 is outside of the absolute value bars, we'll be able to divide it off of both sides. So I get the absolute value of y is equal to negative 3. Now, at this point in time, my absolute value is isolated. So we're going to look at whether or not it makes sense to solve this. And notice on this side, we have a negative number. So because this number is negative, this idea about absolute values being a distance away from 0, you can't have a distance equal to a negative value. So in this case, there's no solution, and I don't have to move forward at all. Now, we've been looking at a lot about if that number on the other side was positive or negative. So, what if, on that first problem, what if I had given you the absolute value of 4x plus 2 is equal to 0? What would we do there? All right, so this distance then is 0, and that does make sense. If you go up to these original 3 problems, you can have a distance equal to 0. That just means you're 0 units away from 0. The thing about this one is that you don't break this into 2 cases, right? We wouldn't do the absolute value of 4x plus 2 is equal to 0 and the absolute value of 4x plus 2 is equal to negative 0, because this idea about negative 0, that doesn't make any sense, right? 0 is not positive nor negative. It doesn't have a sign. So in this one, it does make sense to solve, but we don't break it into 2 cases. The only case that makes sense here is if this expression on the inside, this 4x plus 2, is in fact evaluating to 0 itself. So if that's the case, then I would have 4x is equal to negative 2, divide both sides by 4, so x is equal to negative 2/4, which is equivalent to negative 1/2. So in this case, then I don't have 2 solutions. I just have this one value that would make the absolute value true. All right, so a couple more comments. In this section, we don't really ask you to graph the solutions, but when we get to the inequalities, we will. So let's talk about why we don't ask you really to graph here, but we will ask you to graph later. If I wanted to graph this, so we're going to be on the real number line. Okay, so the point I'm trying to graph is -1/2. So, here's my number line, 0 and -1. So -1/2 is in between 0 and -1. To graph a point, all you do on a number line is you just put a dot. Okay. And then because this is not on a tick mark, I like to label my dot so everybody knows exactly what I'm trying to graph right there. But that's why we really don't ask you to graph, because there's not that much going on, right? It's just a number line with a dot at that point. So this then is it is a visual representation of what's going on here, but we really don't ask you to graph. The other thing I want to mention before we kind of wrap up these absolute value equation examples is just as a reminder, if you wanted to, you could check your solutions and make sure they work. Right? So the check is not mandatory, but it's helpful, especially if you're like, I don't know if I did that right. So if we come back up to our first example, our solution set was 1 and -2. Let's check those values and make sure that they work. All right, so first off, we're going to check x being 1. So in the original problem, I'll have the absolute value of 4 times 1 plus 2. That gives me the absolute value of 4 plus 2, which is the absolute value of 6. So this is asking me how many units is 6 away from 0 on a number line. Well, it's 6 units away, and that is exactly what I wanted it to be, so that works out. Let's check x being -2. So I'll have the absolute value of 4 times -2 plus 2, which is the absolute value of -8 plus 2, which is the absolute value of -6. So now that I have that boiled down to a single number, we can go ahead and simplify that. This is asking me what is the distance that -6 is away from 0 on a number line, and it is 6 units away, which is, again, exactly what I wanted it to be, so that one checks out as well. All right, so if you've got the time, when in doubt, you can check it. So those are going to be your equations. Now let's talk about how things change when we go to our inequalities. All right, so for the first example, the absolute value of inequalities, we'll have the absolute value of x is less than 4. So this is asking me, if I kind of look at structurally what's happening here, because absolute value is a distance, this is asking me what values have a distance less than 4 units away from 0. So visually, I can put down my number line up here. So 1, 2, 3, 4, right? So I'm only interested in going 4 units away from 0. So then 4 units away from 0 on the other side, I'll go up to -4, maybe -5, just for this to have a little bit of extra room. All right, so I want values with respect to 0, which is right here. I want values that have a distance that's less than 4 units away from that value. So that means I'm allowed to maximum from 0 walk 4 units away before I have to stop. So if I walk to the right, I'll be able to walk out to just before I get to 4, and then I have to stop. Okay, so since I can't actually grab 4, I'll put a parenthesis there to say I can't actually be at 4, because I have to be less than 4 units away. And then from 0, if I walk 4 units to the left, all right, so I can walk up to 4 units for the left before I have to stop, I can go out to -4 before I have to stop. And again, I can't actually land on -4 because then I will have gone too far. So what we're seeing here then, for values that have a distance less than 4 units away from 0, the values, which we'll use the variable x here, those values are going to have to be trapped in between 4 and -4. As long as I'm picking values that's within this region, I should be good. Writing this in interval notation, this is written as -4 to 4. So that generalizes to how we set up the less than inequalities in a more generic sense. Okay, so if you have less than inequalities, and it doesn't really matter if it's less than or less than equal to, the setup is the same generic structure, except obviously the equal to part will have an equal to over here. So these ones, I think about just generically what we're going to be doing is we're going to be trapping that, whatever that expression is inside the absolute value bars, we're going to be trapping it about 0. Right, so we're going to be setting that expression trapped in between the positive and the negative of whatever number we're seeing over there. So that is for the less than inequalities. Now for the greater than, let's take a look at this example. The absolute value of W is greater than or equal to 5. So this inequality is asking me what values have a distance that's greater than or equal to 5 units away from 0. Let's try that again. Away from 0. Right, so again, let's kind of come back to our number line so we can see what's going on right here. Okay, so here's 0. And the distance that's in question here is this 5 units away. So I can go 5 units away to the right or 5 units away to the left. And I'm looking for a distance specifically greater than 5 units away from 0. Okay? So with respect to 0, I've got to be more than 5 units away. Well, if I want to be more than 5 units away on the right, that'll be this stuff out here. And if I want to be more than 5 units away to the left, that'll be this stuff out here. Right, to the left of -5. So I end up getting these two distinct regions that have this distance about being more than 5 units away. Specifically, all the stuff to the left of -5 and all the stuff that is to the right of +5. Right, so since I have these two distinct regions, if I wanted to write this in interval notation, this left region is going to be from -infinity up to -5. And then looking at my inequality, my distance is allowed to be greater than or equal to 5 units away. So the equal to, I am allowed to grab -5. So I would have a bracket at those endpoints. So the left region is from -infinity up to -5. The right region goes from 5 to +infinity. And then we'll put a union between the two of them if I want to write this in my interval notation. Alright, so then that tells me how I want to solve these then more generally. If I have that I want an absolute value that is going to be greater than or equal to a certain distance away, that's going to be equivalent to setting up two inequalities. One for the values that would satisfy this left region, specifically u is less than -a, and then or I could have solutions in the right region, which would be u is greater than a. All right, so then this is going to break this into the two cases, where in between the two cases is this word or. So for these cases, I kind of imagine these as being pushed away from 0. All right, so I get these two cases where visually I've got to be far enough away to the left, or I have to be far enough away over there to the right. So that then sets up my two cases. So you can see then for these types of problems, you will need to identify if you are in the less than case because they have one particular setup, or the greater than case because they have a entirely different setup. So let's try a few of these together, seeing what this looks like kind of more generally. So the steps to solve, first again, if the absolute value is not isolated, you will need to isolate it before you can break it apart. Then you're going to write a pair of compound inequalities depending on the direction of the comparison. So kind of as a reminder of what we've done up here, and I'm not going to write the two cases just with the equal part in there because that really is not affecting it. if your absolute value is, the absolute value of u is less than a, this is going to be equivalent to writing negative a is less than u, which is less than a. So that's how you're going to set up those cases. Again, notice that the absolute value bar is broken, and that's what we're trying to do, so that way we can isolate our variable and figure out, the value that's going to make this inequality true. If you have the greater than case, so absolute value of u is greater than a, that is going to be equivalent to setting up two cases. And again, because I have two separate cases, just kind of how I did with the equation stuff, I like to do it on the inequality stuff as well. Here's my two cases. The first case is u is greater than a, and then the second case is u is less than negative a. So for those types of problems, looking at kind of the structure of the two cases I'm setting up, and by the way, between the two cases is the word or. So if this case or this other case is satisfied, it becomes part of our solution set. Structurally, looking at what's going on here, for the first case, this is equivalent to the original problem, just dropping the bars. So that's my easy case. For the second case, this is very similar to what we saw with the absolute value equations. Right? We leave this expression inside the absolute value bars alone, and then this number over here becomes its negative. But a very important thing to pay attention to what's happening on this side is also what's happening to the inequality. It's reversed from how it looks in the original problem. So for these types of problems, when I go to set up that second case, I like to think about this as being called the flip-flip. To set up the second case, what we're going to do is you're going to flip the inequality and have it open up the other way, and you also flip the sign of the number that is on the other side. So one last thing before we start looking at some of the examples is coming back up here, all of these kind of cases are assuming that whatever this number is that you see over here on this other side, that number should be positive in order for these cases to be able to be broken up like this. If that number is 0 or negative, you're going to need to slow way down and think about what's going on inside of that inequality. And we're going to look at a couple of examples of that and talk about why, if there's a 0 or a negative over here, we have to start being very careful. And it comes back to the fact that I'm looking at distances. So distances of being 0 kind of boil down to almost like a single case. So we're going to look at those, and then distance can't be negative. So if I'm asking you about distance as being required to be negative, since that can't happen, that's going to adjust how we think about our solution sets. Okay, so we're going to set up our inequalities depending on the direction of the comparison, solve each resulting inequality, and then write the final answer in interval notation or set notation if you prefer that, and that option is available to you. And then graph the solution if necessary, if you're asked to graph it. All right, so let's get started. Our first example is going to be the absolute value of n plus 2 is greater than 4. So the first thing on this is to pay attention to the fact that this is a greater than inequality. All right, so that'll tell me kind of the way I need to set this up. Now my absolute value is already isolated, so that part's taken care of for me. So now we're going to break it into our cases. So when I have the greater than inequality for my two cases, okay, so for the first case, which is, again, this is going to be the easier one to remember, you're just going to write the original problem, but no absolute value bars. So n plus 2 is greater than 4. Okay, so that's my first case, and I'm going to solve that in a moment. Immediately set up your second case. Don't forget to write it down as part of your kind of initial steps, because otherwise you will forget to set it up later. So my second case, again, what's inside the absolute value bars I don't touch, so it's n plus 2. But on the other side, I'm going to do the flip-flip. So I'm going to have my inequality open up the other way. So as opposed to a greater than inequality, now it's going to be a less than. And then the number that's on the other side right here, I'm going to record it's negative. So since the number was positive 4, I'm going to record a negative 4. That's my second case. The word between these two cases is the word or. So now let's solve these. So for the first case, I'll subtract 2 from both sides. We get n is greater than 2. For the second case, we'll subtract 2 from both sides. We get n is less than negative 6. Now, because I'm very visual, sometimes I find it super helpful just to do a quick sketch of what's going on to write my interval notation. So my two players are 2 and negative 6. So on a number line in the correct orientation is negative 6 and then 2. I don't care about spacing at this point. I'm just trying to get an idea of what's going on here. So n can be greater than 2. So on my sketch right here, here's all the stuff that's greater than 2. Or n can be less than negative 6. So on my number line here is all the stuff that's less than negative 6. So from my sketch then, that helps me write my interval notation. So my interval notation for this left region goes from negative infinity up to negative 6, with a parenthesis at negative 6, and then the infinities always get parentheses. And then union, this right region goes from 2 to positive infinity. Right, so there is my interval notation. Now, just as a side note, if you had written your interval notation from 2 to infinity, union negative infinity to negative 6, kind of how you're seeing it presented at these two answers going from left to right, that would be fine as well, because we can show using set operations that this union idea is commutative, so these two are equivalent ideas. But I always like to record my intervals going in order from left to right, so I'm mimicking what's happening on the number line. Okay, so they did ask me to graph the solution set as part of my answer. So at this point in time, here's where then I can come back up to what I was doing earlier just from my sketch and then go ahead and flush it out. Okay, so at negative 6, I will have a parenthesis. At 2, I'll have a parenthesis, and then just put arrows at the end of my shading. There's my graph. Alright, let's take a look at our next example. The absolute value of m minus 2 is less than or equal to 1. Alright, so in this case, then, because this is a less than inequality, and this number over here is positive, what we're going to do is we're going to take this expression inside the absolute value bars, which is m minus 2. Don't change the sign of the operation inside of there. Right? The absolute value bars is not making that minus become a plus. Right? That's not what absolute value is doing here. Absolute value is a distance idea. So this is then saying what values for m can I put in this expression such that when I compute it and I find the distance of that resulting number, that distance is less than 1 unit away from 0. So because of this less than idea, I'm going to be trapped about 0, which means that this expression, I want to trap it in between the positive and the negative of the number that I'm seeing right here. So I get the inequality, negative 1 is less than or equal to m minus 2, which is less than or equal to 1. So let's go ahead and solve that. We'll add 2 to all the regions. Right, so add it to the middle region, left region, and right region. So I get 1, which is less than or equal to m, which is less than or equal to 3. Right, so this is a compound inequality involving the word and. The values for m have to satisfy both inequality restrictions. M has to be greater than or equal to 1, and simultaneously m has to be less than or equal to 3. So as an interval, that's going to give me all the numbers between 1 and 3, and because of the equal sign, I'm going to have brackets right there. And so we can see this on a number line. Okay, so there's my real number line. I'm going to shade all the numbers between 1 and 3, and then have brackets at those endpoints. All right, here we go. There's my graph. Okay, so let's take a look at our next example. So we have the absolute value of 2x minus 5, close the absolute value, plus 2 is less than 9. So for this one, my absolute value is not already isolated, so the first thing I want to do is isolate it by subtracting 2 from both sides. So I get the absolute value of 2x minus 5 is less than 7. Okay, so since this is a less than inequality and this number over here is positive, it does make sense to solve this. So I would encourage you to take a moment right now on your own, finish this problem, solve it, find what the solution region is, and then graph it, and then check it against the solution that I'm about to do right now. Alright, so because of this less than idea, what we're going to do with this 2x minus 5 expression is we're going to trap it in between the positive and the negative of the number that I'm seeing. And at that point in time, the absolute value bars drop. Alright, which is super cool because now I can start moving stuff around. So first we're going to add 5 to all regions. So I would get negative 2 is less than 2x, which is less than 12. And then we'll divide 2 by all regions. So then I get negative 1, which is less than x, which is less than 6. So for my solution set, then x is going to be trapped between negative 1 and 6, but all values in between. So as an interval notation, negative 1 comma 6 with parentheses on both of those values. And then for my graph, alright, so this isn't going to necessarily be to scale, but there's negative 1 and 6. We'll put parentheses on both of those endpoints. And let's shade all values in between. Alright, cool. There's my graph. Okay, so let's start talking about some of our unusual cases. So for the next one, it's the absolute value of 5x plus 2/7, close the absolute value, is less than or equal to negative 4. So the first thing I want you to notice is the absolute value is already isolated, so that step is done. But then when we get to the second part where we're going to write our inequalities depending on the direction of the comparison, for this one we want to kind of stop and take a moment because this number over here is negative. Okay, so we want to watch out. Okay, when we're dealing with absolute value, which is a distance idea, and we see negatives pop out, there's where we need to slow down and watch what we're doing. Now, the cool thing on this one is there's really not that going to be anything for us to solve or set up algebraically, but the bad thing is you will need to slow down and kind of think about what's going on here. All right, so remember absolute value, what's going to happen over here on this left side. Absolute value is always going to produce something that is either positive or it could be 0, but basically it's going to be non-negative. Right? I don't care what number you give me for x, and we can actually find values that would satisfy these different characteristics, but different values for x in here, once I take the absolute value of that left side, the output is always going to be a positive number or it's going to be 0. What if it's a positive number? Let's take a look at what's going on with our absolute value and the inequality that we were given. The inequality is less than or equal to negative 4. If I can get this left-hand side to output something positive, is a positive number going to be less than or equal to negative 4? No, right? Never. A positive number is not going to be less than a negative number, right? So that doesn't make any sense for me to even try to find values that would satisfy the less than idea or the equal to idea, right? Because a positive can't equal a negative. What about 0? What if I can get this left-hand side to produce a 0? Is a 0 ever going to be less than or equal to negative 4? Well, no. Again, right? 0 is not going to be less than negative 4, and 0 is never going to be equal to negative 4. So it doesn't really matter what I find for x. When I go ahead to compute it, this left-hand side will never be less than or equal to negative 4. So for this problem, then, we're finding it's no solution. All right, So just maybe as a more general note then, what we're finding is if you have the absolute value of some expression and you want that to be less than a negative number, and it doesn't matter if it's less than or equal to or less than, it's the same idea that kind of applies. This will always have no solution because it's kind of like a nonsensical thing that we're asking here. This left-hand side, where the absolute value is, it was never going to be less than a negative number. Now you might be asking, well, what if it wasn't less than? What if it was greater than? That's a great question, and we will look at an example of that in a moment. Before talking about the greater than ones, though, I want to talk about what happens if we start throwing out some zeros, right? Because I said we have to kind of slow down if it's a negative number over on the right-hand side or if it's a zero. So here, let's take a look at our next example. The absolute value of, in the numerator, 5 parentheses x minus 3, close parentheses, all over 2, then close the absolute value, is less than or equal to 0. Okay, so for this one, because what's going on this side right over here is a 0, and again, notice that the absolute value is already isolated. All right, if it wasn't already isolated, I would have to isolate it first before I start thinking about all of this stuff. But because it's isolated and I'm seeing a 0 over on this side, again, I want to kind of watch out. We need to slow down and really think about what's going on here. Okay, so on this left-hand side, again, because of the absolute value, this side is always going to be a positive number or it can produce a 0. So let's think about those just two generic cases. What if I can get this left-hand side to produce a positive value as a result of the absolute value? Is a positive number going to be less than or equal to 0, which is the condition I need to satisfy for my inequality? No, that doesn't make any sense. Right? A positive can't be less than or equal to 0. What if I can force this left-hand side to give me a 0? Is 0 less than or equal to 0? Well, yes. Not less than, right? 0 is not less than 0, but 0 is equal to 0. This is the one that makes sense. So let's go ahead and find out then what value for x makes this side equal to 0. So 5 parentheses x minus 3 all over 2. There's that inner expression inside of my absolute value. I want to find what value for x makes this equal to 0. So that is something we could solve. So let's go ahead and solve that. We'll multiply both sides by 2. So I get 5 parentheses x minus 3 is equal to 0. You could distribute through, but I'm just going to go ahead and divide both sides by 5, which gives me x minus 3 is equal to 0, which means x is equal to 3. Now, I want you to notice that the original problem was an inequality, but the thing I'm solving right now is an equality, right? That's an equation. So in this case, then, I don't write my answer as an interval because it's not a whole bunch of values that will work. It's just this one value. The only value that will make this an inequality makes sense is if x equals 3, and it will satisfy the equal part of my inequality. So in this case, I don't write it in an interval notation. I would write it in just set notation. Right? So a solution set, I would just put the 3 inside the braces. And then if you wanted to graph this, this is kind of the dinky case to graph. Right, so I'll just put down a number line with just a couple of values on there, and then at the value in question, which is 3, I'll put a dot. Okay, so there's the graph of the solution set. Alright, so we can see here that with the 0 on that one side, we had to be careful and kind of watch out. Now, let's go on to some what-if scenarios as an extension from that. What if the problem that you had been given was the absolute value of 5 parentheses x minus 3 all over 2 is strictly less than 0? What if it didn't have the equal to sign on there? How does that adjust how I would find and express the solution if there is one. Now, again, remember that's going to happen on this left-hand side. This is always going to be positive, or it's going to be 0 as its output. That's the only thing absolute value can give me. What if I can get this to give me some positive number? Is a positive number going to be less than 0? No. What if I can get this side to give me a 0 as its output? Is a 0 less than 0? No. So it doesn't really matter what positive number I get out or what 0 it gives me. I can't ever satisfy the inequality that this output on the left-hand side is going to be less than 0. So in this case then, we would conclude that there's no solution. Right? So, and neither case is going to be ever satisfied by what's going on there. Now, we talked about zeros being tricky. Here's another what if. What if it was the original problem, but what if I wanted it to be greater than 0? How does that change things? Okay, so again, there's really not going to be too much to solve for on here. We just have to think through our cases. So what's going to happen on this left-hand side is this is going to either produce for me some sort of a positive number, or I can actually get 0 as an output. What about if I can get this left-hand side to produce a positive number? Is a positive number greater than 0? Yes, always. It doesn't really matter what that positive number is. It's always going to be satisfying that the left side is greater than the right side. What if I can get this side to produce a 0 out? Is a 0 greater than 0? No, right? Okay, so that's going to be then a scenario that I have to avoid. I have to avoid getting a 0 out on this side, but any other number would work because it's going to produce a positive output. Well, I already know what's going to be the value that's going to produce a 0 out, right? In order to get the 0 out on this side, that's what we did earlier, we found x would have to be 3. So any other number in the entire universe would work except for 3. So in my solution set then, how I would write that is negative infinity up to 3, union 3 to positive infinity, and then make sure you put the parentheses on the 3 because we have to make sure to exclude that because that value doesn't work. Okay, just for fun, one more what if. One more. What if absolute value of 5 parentheses x minus 3 all over 2, close the absolute value. What if it was greater than or equal to 0? What if that's what I was given? Okay, so again, this left-hand side is either going to be a positive number or it's going to be a 0 as its output. A positive number, is that going to be greater than or equal to 0? Yes. That will always be satisfied. What if I can get this side to produce a 0? Is a 0 greater than or equal to 0? Yes, it'll satisfy the equal to part. So it doesn't really matter what I get out on the left-hand side in terms of its actual numerical quantity. It's always going to satisfy the left-hand side is greater than or equal to 0. So in this case, any number for x would work, and my solution set is negative infinity to positive infinity. So again, on these what-if cases, there's really nothing to solve, but you do need to stop and think about what you're given and what's going to satisfy the absolute value expression that you are trying to work with. Okay, so enough of those digressions. We had worked with this problem earlier where I had a negative on this side with this less than or equal to inequality, and I had said, well, what if it was greater than? We'll look at an example in a moment. Well, here it is. Okay, so our next example is the absolute value of x plus 1, close the absolute value, plus 11 is greater than or equal to 9. Now, notice that the absolute value is not isolated, so the first thing we're going to need to do is we're going to isolate that absolute value by subtracting 11 from both sides. We get the absolute value of x plus 1 is greater than or equal to negative 2. Alright, so here's where we have to be careful. Right? I've got a negative number on this side. Okay, so again, we're going to need to watch out and pay attention to what we're doing here. There's nothing for me to really set up to solve this problem. I just need to think it through. This absolute value side is either going to produce for me some sort of a positive number, or it's going to produce for me a 0. Because it's the distance requirement, that's the only things I'm allowed to get out on that left-hand side once the absolute value is isolated. Let's take a look at the inequality that I'm trying to satisfy. Is a positive number greater than or equal to -2? Yes, always. What if I can get this to produce a 0? Is a 0 greater than or equal to -2? Yes, always. So it doesn't really matter what this number is that this absolute value produces. It's always going to be something that's bigger than or equal to -2, specifically bigger than, because the smallest this side could ever be is 0. So in this case, my solution is from -infinity to +infinity. Any value works for that variable x. The graph for this kind of looks a little weird because you want to shade everybody, alright? So I just kind of put down a generic number line with just a couple of values on either side of 0. Alright, so there's my generic number line, and then just come on here and shade everything a little heavier so it's really clear that I'm shading that stuff, and then put arrows at the end of your shading to indicate, yep, and I'm going to go forever in both of those directions. Right? So that's what the graph for that would look like. Right, so what we're seeing on those ones, kind of as a general case, is if I have the absolute value of some thing, I'll just write it as u, and I want that to be greater than some sort of a negative number. So that is going to boil down to -infinity to +infinity. I don't want you to sit there and memorize that. I want that to make sense to you, why that's going to be the case. When you have the absolute value and you have a negative on this side, why is it going to be this infinite solution case? That should start making sense. Okay? But in general, that's what we're going to have there. Okay, so one last example. Here's an absolute value over here. Absolute value of x over 5 minus 3, close the absolute value, -8 is greater than or equal to -4. Now, a lot of students will then say, hey, I have an absolute value. I've got a negative number over here on the other side of the absolute value. Those are the cases that we have to be careful of because of the nature of what's going on in this case. This is going to be my -infinity to +infinity case. And they just put that down and they move forward. You can't make those determinations if your absolute value is not isolated. So the first thing we need to do is we need to isolate our absolute value. Okay, so we'll add 8 to both sides, and then we have something that we can assess the validity of and set up and solve. So this is something that we can solve. Right? I get the absolute value of x over 5 minus 3 is greater than or equal to 4. So I'd encourage you to take a moment right now, see if you can remember what you need to do to set that up and solve it without referring to your notes on the other side. Now, don't be surprised if you're like, wait, but I don't remember that, because we've talked about a lot of stuff since then. But that's the point you need to get to, is you need to start remembering, hey, if I have an absolute value and the greater than inequality, what do I need to do to set those up? Alright, so this is going to then be the one of the greater than, because you're being pushed away from 0. This is the one that you have to set it up by breaking it into two cases. So I'll have x over 5 minus 3 is greater than or equal to 4. So it's the original problem, just drop the bars. And then I'll have x over 5 minus 3 is less than or equal to -4. Okay, so that case is my flip-flip case. Alright, so we're just going to solve each one of these separately. Add 3. So I get x over 5 is greater than or equal to 4. Multiply both sides by 5. X is greater than or equal to 20. No, hold on, I'm looking at this. I said add 3, but I didn't actually add it on that side. So x over 5 is greater than or equal to 7. Yeah, that makes more sense. Then we'll multiply both sides by 5. x is greater than or equal to 35. All right, other case, add 3 to both sides, x over 5 is less than or equal to -1. Multiply both sides by 5, x is less than or equal to -5. All right, so if it helps for you to graph this before you write your solution in interval notation, you are welcome to do that. All right, so my players are -5 and 35, and again, this isn't necessarily going to be to scale with any of the numbers in between. I want to shade all the stuff that's less than or equal to -5, so here's all the stuff that's less than -5. It's going to be to its left. At -5, I'll put a bracket. All the stuff that is greater than or equal to +35, well, here's the stuff that's greater than 35. It's going to be to the right. At 35, I put a bracket. And then my solution in interval notation is from -infinity up to -5, bracket, union, bracket, 35 to +infinity. Now, if you wanted to write that in your solution set, that would look like the set of all x's such that, and again, I like to record them in order for how they're going to be on the number line, but it really doesn't matter just as long as I have both of them. X is less than or equal to -5, or x is greater than or equal to 35. Right? So that's what it would look like if I wanted to write it as a solution set. And just one final note about how to write the answers. Sometimes students will try to write this answer as opposed to writing 2 inequalities, they'll try to put it into one line like we were doing with those less than ideas, and they'll write so the 2 conditions I need to satisfy is x is greater than or equal to 35. Okay, so there's that idea. And then they'll try to attach the other inequality to this, which is x is less than or equal to -5. Okay, so here's my x, so this one is the less than. Okay, so I'll have the pointy end pointing toward the x, right? And here's my -5. So writing it in one line, it looks like this. -5 is greater than or equal to x, which is greater than or equal to 35. This is incorrect. This is a bad way to write what's going on, because in math, we read everything on one line as true. So the whole string of relationships has to hold true. So if you write it like this, you are saying, if we kind of read what's going on with the end pieces, you are saying that -5 is greater or equal to 35, which obviously is not true. So you cannot write your inequality like this all in one line. If it's this greater than case, you have to break it into 2 intervals, or when you're writing the interval notation, make sure you put the union in between them. If you're writing it in the set notation, just put the word or between them. All right, so for these absolute value inequalities, you do need to be a little bit careful, kind of back up to the beginning. So you'll need to immediately pay attention to if your absolute value is not isolated, because if it isn't, that's your first step. And then once it's isolated, you'll need to pay attention to if it's a less than inequality, because that's going to be set up one way, or if it's a greater than inequality, it's going to be set up an entirely different way. If the number that's on the other side of the inequality is a 0 or a negative, you'll need to slow down and kind of think about your cases, about what will make sense or not make sense. And some of those problems, that's where you're going to get either the possibility of a no solution. In some of the cases, depending on what's going on, we'll have our infinite solutions. And then in some cases, especially involving those cases with a 0, you might only have a single value that would work to satisfy what's going on.